All right, video notes today. The idea with video notes are that you are to look and listen without writing anything. That way we don't miss anything in the presentation. Then when the pause sign comes up, you pause the screen and then copy down the notes. All right, we're on still finishing up chapter 15. Last thing we were talking about was sound waves. Sound waves are longitudinal waves, and they're caused by vibrations. Every sound has to have some vibrating object causing the sound, and that vibrating object is actually hitting the air molecules and causing this longitudinal wave or compressional wave to move through the air to your eardrum, which makes it vibrate as well. All right, what we need to realize about the sound waves is that those frequencies are all the same. The frequency of the sound source, the frequency of the sound, and the frequency of your eardrum are all the same frequency. We're also talking about resonance, is when outside force causes an object to vibrate at its natural frequency. Easy examples, if I take a glass and hit the edge with a spoon or rub my finger across the top, that glass will vibrate at its natural frequency. Right? There's also musical instruments that work the same way. By pulling the bow across the strings on a violin, you're causing the string to vibrate at its natural frequency for that particular length of string. All right, pause and copy. Next topic is pitch. Pitch is the human perception of frequency for sound. We'll learn in the next chapter that color is the human perception of frequency for light. For our sound waves, we know that a higher pitch is caused by a higher frequency. That means that there is more waves per second to make that higher frequency. All right, the human hearing range goes from 20 hertz up to 20,000 hertz. Sounds below 20 hertz are sounds that you cannot hear. They're called infrasonic, and that prefix infra means below, so it's below our audible hearing range. Sounds that are higher than 20,000 hertz are also sounds you cannot hear. These are called ultrasonic, and that prefix ultra means above, so this is above our frequency range. Now all the sound waves go through air, and air has a constant speed to it, somewhere around 340 meters per second. Because we're in one medium, we're not changing mediums, the speed stays constant, and that means the wavelength and frequency are inversely proportional to each other. So for our infrasonics, that means they have a low frequency or a long wavelength. For ultrasonics, they have a higher frequency and a shorter wavelengths. Now these two relationships are things that you have to have memorized. All right, higher frequency, shorter wavelength, you need to know that. For light waves, that also means they have higher energy as well. Lower frequency goes with longer wavelength. All right, pause and copy. All right, next topic is a Doppler effect. This is apparent frequency change due to the relative motion between the observer and the sound source. All right, that phrase relative motion means one or both can be moving. The object observing and the object that's the source. So the source can be moving towards or away from you. You hear a frequency change, or you could be moving towards or away from the source. You would also hear a frequency change, or both of you could be moving. All right, this animation shows a sound source in the center, and we have sound waves coming out in all different directions. Notice that the distance between these waves, the wavelength, stays constant as the sound waves travels. And that means you could be anywhere and you would hear the same sound, the same frequency. However, this changes when the object starts moving. If I move that object forward, you can see it's moving along towards the sound waves in the forward direction. So on this side, these sound waves get crowded together, and you can see the distance between them is actually smaller. We have a shorter wavelength on this side. That means if I'm standing on this side, a smaller wavelength means a higher frequency that I would be hearing. If I'm over on this side, the wavelengths are spread farther apart, and that means I would be hearing less waves per second, a lower frequency or a lower pitch sound if I'm on this side of the object, if it's moving away from me. All right, so this is the formula for the Doppler effect. Lots of letters on this one. The FO stands for what the observer is hearing, and that's the whole point of the formula, is to figure out what do you hear when something's moving. It doesn't sound at the original frequency. All right, Fs is the frequency of the source, and that's the original sound that's being coming out of the source before it starts moving. And then we have three different velocities to look at. The one that's just the regular v is the speed of sound. VO is for the speed of the observer, and VS is the speed of the source. Right? Now that speed of sound, we're going to use 340 meters per second if they don't tell you what the speed of sound is that particular day. For the speed of the observer and the speed of the source, we need to pay very careful attention to these because these can be positive or negative numbers. Right? And the convention we use, if the object's moving towards the other one, it has a positive speed. If it's moving away from the other one, it has a negative speed. All right? So for example, the observer's moving towards the source, he has a positive speed. The source is moving away from the observer, he would have a negative speed, and vice versa. All right, stop and copy. All right, so let's look at an example. Example, the train here, we know when the object's moving towards you, it has a higher pitch to it, and when the object's moving away from you, it has a lower pitch. Our example problem today, we're just going to look at the train moving away. It says the train's traveling at speed of 75 meters per second and has a frequency of 85 hertz for the whistle. The speed of sound that day is 340 meters per second, and we want to know what frequency does this observer hear as the train moves away. So on all of our problems, we start off by listing down the given information and labeling the variables that go with it. The frequency of the source is the train, and that is 85 hertz. Speed of sound that day, 340 meters per second. The speed of the source is 75 meters per second. And when you're reading these problems, you need to watch out for keywords such as moving away. If that train is moving away from you, it has to have a negative velocity. Or if you were moving away from the train, you would also have a negative velocity. Right? The other key word in this paragraph is the word stationary. If the observer is stationary, that means his velocity is 0. All right, so let's plug these numbers into the Doppler effect formula. Looks something like this. And notice on the bottom we have a subtraction sign in the formula, and we also have a negative sign from the object, the train moving away from us. So when you're subtracting a negative number, you're actually adding these numbers in the denominator to get a larger number. All right. Looking at these numbers as a ratio, we can see that this is less than 100%, and we're going to get a sound that is lower than 85 hertz. So canceling units and rounding off, we get 70 hertz is what is heard from the train moving away. After you do a problem, you have to ask yourself, does your answer make sense? All right. We know that if it's moving towards you, it should have a higher frequency. If it's moving away, it should have a lower frequency. You want to double check and make sure your answer makes sense, because this is our only way of checking. Maybe you got a plus and minus sign in the wrong place in the formula. All right. Pause and copy. All right, so there's a couple things I need to point out here. This is a formula that I've given you. The Glencoe formula is a little bit different. They use the letter D for detector instead of observer, but they also have a different sign in the top of their formula, and it's because they're using a different sign convention. I would like you to do the problems my way because my sign convention is going to come up in some future problems in a different chapter with a different topic, and if you've already learned my sign convention, then it'll make those other problems easier. The worksheet that I'm having you do today also has the formula a little bit different. They're using F for the frequency that you hear and FO for the original frequency, which sort of makes sense, but you have an O up here for observer. I want the other O to stand for observer, and so I changed it to make it this way. So on the sample problems on the worksheet, they're going to be using this formula, and so their FO means something different than my FO, which means something different than most people's FO.